Hey everyone and welcome. Today we are diving deep into the world of X-rays. Now this is a super important topic for both JEE and NEET, so let's get right into it and explore what makes these invisible rays so incredibly powerful.
So, let's kick things off with a pretty simple question. Have you ever actually wondered how doctors can see a broken bone so clearly right through your skin and muscle? Well, the answer, of course, is X-rays. And today, we're going to break down all the science behind this amazing technology.
Here's our game plan. We'll start with the absolute basics. Then we'll look at how X-rays are actually made, compare the two different types of spectra, which is crucial. Then we'll look at two very important laws and finish up with some real-world applications. By the end of this, you're going to have a really solid grip on the whole topic.
All right, let's jump right into our first section, the basics. First things first, what exactly are X-rays?
So, at their core, X-rays are a type of electromagnetic radiation. You know, just like the light we can see. But here's the key difference. They have way more energy and a much shorter wavelength. And it's this high energy that lets them pass right through soft stuff like skin, but gets stopped by denser things like bone.
Okay, and this brings up a really important distinction you need to know. Soft versus hard X-rays. It's pretty straightforward, really. Soft X-rays have a longer wavelength, which means lower energy, and so they don't penetrate very well. Hard X-rays are the opposite. Shorter wavelength, higher energy, which gives them some serious penetrating power. This difference is a really key concept for your exams.
So, we know what they are, but how do we actually create these powerful rays? Let's take a look at how they're produced.
The whole process happens inside this special vacuum tube. It's called a Coolidge tube. So here's what goes down. First, a tiny filament gets heated up and it starts boiling off electrons. Then, a massive voltage kicks in and blasts these electrons at incredible speeds towards a metal target. And finally, when those super fast electrons slam into the target, they stop or decelerate, like instantly. All that kinetic energy has to go somewhere and boom, it's released as X-rays.
Now here's the most important part of that collision. When those electrons hit the target, X-rays are actually created through two totally different processes. And understanding these two is what our next section is all about.
Okay, let's really dive into what is probably the single most important part of this topic for your exams, the difference between the two types of X-ray spectra. A lot of questions are going to come from right here.
So the first type is called Bremsstrahlung. It's a German word that literally means braking radiation, which is a perfect name for it. This happens when an incoming electron zips past the nucleus of a target atom and gets deflected, so it slows down or breaks. This produces a whole continuous range of X-rays. The second type is called characteristic radiation. This one's different. It happens when an incoming electron comes in with so much energy that it completely knocks an electron out of one of the inner shells of the target atom. Then, an electron from a higher shell drops down to fill that empty spot, and when it does, it emits an X-ray with a very specific single wavelength. And this graph shows you exactly what that looks like. You see that smooth, broad curve underneath? That's the continuous Bremsstrahlung spectrum. And then, sitting right on top of it, you have these super sharp peaks. Those are the characteristic X-rays. And here's the cool part. Those peaks are in a different place for every single element. They're like a unique fingerprint for the target material.
Now, one really important thing about that continuous spectrum is that it has a sharp cutoff. There's a minimum wavelength, and you just can't produce any X-rays with a shorter one. The formula for it is lambda minimum equals hc over EV, where that V is the accelerating voltage. And you have to remember this cutoff depends only on the voltage. It has nothing to do with what the target is made of. This is a super important formula for solving problems.
All right, next up, let's get into two laws that you'll see pop up all the time in JE and NEET, Moseley's Law and Bragg's Law.
Moseley's Law is all about those characteristic X-rays we just talked about. It basically says that there is a direct relationship between the frequency of those X-rays and the atomic number, Z, of the element that's making them. The formula looks like this. The square root of the frequency equals A times Z minus B. And let me tell you, this discovery was an absolute game changer. And here's the proof. This graph plots the square root of that X-ray frequency against the atomic number Z. And what do you see? A perfectly straight line. This is the visual evidence that shows the beautiful, linear relationship that Moseley's Law predicted. You know, it's hard to overstate how huge this was for chemistry. Before Moseley, scientists arranged the periodic table by atomic weight, and it had some weird problems, like argon and potassium being in the wrong spots. Moseley's law proved that the most fundamental thing about an element is its atomic number, the number of protons, not its weight. It basically fixed the periodic table.
Okay, our second big law is Bragg's law. This is the absolute foundation of a field called X-ray crystallography. When you shoot X-rays at a crystal, they bounce off the neat layers of atoms, and they diffract. Bragg's law gives us the exact condition for when those reflected waves will add up perfectly. The formula is n lambda equals 2d sine theta, where d is the spacing between the atom layers and theta is the angle the X-rays hit out.
The derivation is actually just some simple geometry. Just picture two parallel X-ray beams. One hits the top layer of atoms, and the second one goes a little deeper to the next layer. So that second ray has to travel an extra distance, right? Well, that extra path it travels is exactly 2d sine theta. And for the waves to line up perfectly and create a bright spot, that extra distance has to be a whole number multiple of the wavelength, or n lambda. Put it all together, and there you have it, Bragg's law.
So what does this look like in the real world? Well, here you go. This is an actual X-ray diffraction pattern. Every single one of those bright spots is a place where Bragg's law was satisfied. By measuring the location of all these spots, scientists can work backwards and figure out the precise 3D arrangement of every atom in a material. It's incredible.
Okay, so we've covered what X-rays are, how we make them, and the laws they follow. Let's wrap things up by looking at why all of this matters so much in the real world.
Well, the most obvious one is medical imaging, like we talked about at the very beginning. But there's also X-ray crystallography, which, by the way, is how we discovered the double helix structure of DNA. It's also used to identify materials since every crystal has its own unique diffraction pattern. You see it every day in airport security scanners, and it's even used in radiation therapy to treat cancer.
There's no doubt that X-rays completely changed science and medicine. It kind of makes you wonder, what's going to be the next big discovery that changes our world so completely? Something to think about. With that, I want to wish you all the very best for your exams. Keep working hard and keep learning.